My name is Reza. I'm a PhD student at Sharif University of Technology at Iran, and I'm a visiting researcher at Polytechnic Montreal. My research is a study on upper extremity control on a lower extremity exoskeleton in walking of users with paraplegia. So, in the recent years, so many exoskeletons have been developed for the people with paraplegia to walk, and even some of them have been commercialized for the individual persons or clinics to buy and to service people with it. But the first question that we should ask ourselves is what these devices have achieved for these people. First of all, in compare with conventional orthoses, these devices made walking for these people much easier. They require much less effort to walk with these devices, and even there are some people that they cannot walk without with the conventional orthoses, but they can walk with exoskeletons. And besides that, these devices improve the walking performance of people with paraplegia. They can walk much faster with exoskeleton rather than with orthoses. And besides all of that, these devices give these people health benefits, physical health benefits like improving their bone density, reducing muscular atrophy, reducing spasm, uh, improving cardiorespiratory functions, and they gave them mental health benefits. They are really happy when they can walk with these devices after so many times. They feel self-confidence when they can make eye contact with other people. But despite all of these benefits, there are some serious shortcomings that limited the usage of these devices among people with paraplegia. First of all, as Amandine see herself that a few people can work with these devices really independently without the help of the others. And the working with devices also is very much effortful. They tire really fast when they work with these devices, and it is not a device to use them very regularly. Uh, as I said, they have better working performance than conventional orthoses, but they have poor working performance in compare with natural gait. They work really slower than that. They even work slower than moving with wheelchairs. They are really hard to learn. For a device like Reebok, the 40 session training, about a 40 session training is required to the patient or to user to can walk, to be able to walk independently. And there are even some users that they cannot learn to walk independently after that. And these devices are still not completely safe. There are reports that some fractures happened, or still there is a major risk of falling with these devices. And at last but not least, these devices are really expensive to buy, at least $100,000 up to $200,000. So, uh, what can we do? What can we engineers do to overcome these shortcomings? The problem here is that the dynamics, the rules that govern the exoskeleton is not really cleared or is not really discovered yet. So we engineers in this time develop computational models, mathematical equations that describe the system, and these models are developing computer softwares to do engineering analysis task. There are a lot of models in, like, if you want to describe a mechanism or a car crash or fluidics of a fan blade, or even a human body walking on a flat surface. So, can we develop a model for a user walking with an exoskeleton, First of all, what we mean about a model? When we talk about a model, we mean a box that gets exoskeleton design parameters as input, then the gait pattern that moves the actuated joints of the exoskeleton, and the user's properties, its height, its weight, and its outputs, the walking performance of the system, how fast the system is walking, the balance quality, how good the system is keeping its balance, and the user's effort, how much effort the user is consuming to work with the device. It is not the first time that someone tries to develop a model for the user exoskeleton system, but there is a big unanswered question that really made these models really not useful. What is the challenge for developing models for the exoskeleton? Biped walking, when we walk, is mainly related to the lower extremity. We walk with our legs. But when a person with paraplegia walks with an exoskeleton, like what you see in the picture, like most of the exoskeleton that are developed and commercialized, usually there are not enough actuations in the lower extremity degrees of freedoms. What do I mean? Like this exoskeleton, only the hips and knees degrees of freedoms, as some of you mentioned before, is actuated, and the ankles don't dorsiplantar flexion, hips abduction, adduction, or even in ankles inversion. These are not actuated like what we have in a human body. So because of that, lower extremity cannot control mostly the balance, and mostly the side balances cannot keep the balance in the sides, and it cannot control where the system is going. It cannot control if the system is going to the left or to the right. So the user's upper extremity must control lower extremity balance and path following with assistive devices like a pair of crutches or walkers or a cane, or even walking in the parallel bars, to control the balance and path following of the system. So the big unanswered question is here: how the user's central nervous system, or CNS, generates upper extremity motions and torques to keep balance and follow a desired path. And if we answer this question, then another unanswered question can be answered, and that is how is it possible to evaluate the performance of a gait pattern, a given gait pattern to the exoskeleton, or a design of exoskeleton with respect to users' abilities. So, what we are trying to add to the subject of the models for the human exoskeleton systems, first of all, we try to develop a mathematical model for the dynamics of the human users and an exoskeleton, including a lower extremity and upper extremity. Lower extremity consists of the user's body with passive joints, because the user is a person with paraplegia, and a lower extremity exoskeleton attached to the human body. And in the upper extremity, we have the upper extremity of the users that have active joints. We consider that the user is a person with paraplegia, not quadriplegia, so it has active joints, and a pair of forearm crutches. Then we develop a simple controller for the lower extremity. I mean simple because this controller only gives a moving pattern for the knees and hips flexion extension joints to move with it. So what is our second goal? Our second goal is a control logic for the CNS that gets observations from both upper extremity and lower extremity, and it calculates to keep the balance and follow the desired path. What we have achieved until now, the dynamics of the lower extremity is developed based on the general exoskeleton and human body. Also, the dynamic model of the upper extremity is developed implemented by deep reinforcement learning model. The control model is trained in basic standing postures. Here we can see a video that the model is untrained, so it falls after a few seconds. Then you can see here the model that is learned to stand by itself. Then here is the model when it's learned to do a weight shift task when a robot lifts one of each leg at a time. So, what is still to achieve? The control model of the CNS must be trained in working conditions, and the performance of the control model of the CNS must be compared with a real human subject. Should we continue or should I
Yes,
continue?
please.
Okay. So what is required for the validating and training of this model? First of all, we need an exoskeleton that is proof that people with paraplegia can walk with it. Test subjects, what are conditions for test subjects? First of all, we need at least one up to 5 participants with complete spinal cord injury below the level that is eligible to use the exoskeleton, preferably trained to walk with the exoskeleton. What we mean about trained, it can perform sit to stand and stand to sit functions, stand balance for 1 minute with 2 crutches, walk 10 minutes in less than 10 meters in less than 2 minutes, and walk more than 30 meters in 6 minutes. If it's not, if he or she is not trained, he or she must have sufficient upper body strength to operate the exoskeleton, and preferably with variety in gender and weight and height properties. Then we need a gait analysis setup. The required setup must have 3D motion capture systems and markers or IMUs to measure the movements of both lower extremity and upper extremity parts. Force plates and strain gauges to measure the ground reaction forces of the feet and the crutches. So if we have this setup, what should be measured? First of all, the exoskeleton structural parameters are required, like dimensions, mass properties, should be measured on exoskeleton. Test subject properties like overall mass and height and segments lengths. Movements of lower extremity and upper extremity parts during walking, so it can be used to gather joints movements, and ground reaction forces during the walking. What is analysis to be done for the training? For the training, first of all, the dynamic model must be tuned with the parameters that are measured from the real exoskeleton. Then the gait pattern must be extracted from the active or the real exoskeleton. Then it must be fed into the model of the exoskeleton, and based on that, the model of the CNS can be trained in walking conditions. You can see here if and a step of training to learn to walk, but it fails because it's not a the model is not based on a real exoskeleton, a real gait pattern. So what analysis is to be done for the validating? First of all, the user's dynamic model must be tuned with the parameters gathered from the real users. The motion and active torso of upper extremity of joints of both real subject and the model must be extracted, and they must be compared together to validate the performance of the model. Thank you for your attention.